Hello, everyone. Welcome to this week's Crunch seminar. Today we have two speakers. Our first speaker is Antonio Lara Benitez. He is a PhD candidate at Rice University in the Department of Computational and Applied Mathematics, and he's currently in his fifth year. So he's working with Professor Martin B. de Hoop. His research focus is on scientific machine learning, and his educational background, he did his master's in mathematics and applied mathematics and systems research institutes at UNAM in Mexico. Antonio, thank you so much for your time today. We're all looking forward to your talk, and with this short introduction, you can start whenever you are ready.
Okay, thank you. So I appreciate the invitation. Please, at any moment, you can stop me if you have any question. I'm very happy to do it. So my work, hopefully this work, yeah, it's about neural equilibria for long-term prediction of nonlinear conservation laws. I wanna spend some time just to mention all my collaborators and my advisor, Martin de Hoop. So let's go. So the key points I want to discuss here is that we are interested in the predictions, long-term prediction or nonlinear conservation systems. And I'm very sure that for people in this audience, I don't need to be very specific of how complicated this really is. But just to mention 3 points that make it very complicated are the presence of discontinuities. And for instance, I'm talking about shocks, the need to resolve fine scale features, and the sheer size of the nonlinear PDEs. So like consider MHD, we have 3 equations for the velocity, we have to solve the 3 equations for the magnetic field, we have the divergence free of the magnetic field, and it depends if it is incompressible or compressible, you need to keep track of the density, or you need the divergence free. So the amount of equations that we have is like huge. So what I'm gonna discuss, a point I think has been overlooked in machine learning, is that the fact that these equations are presented at the microscopic level. However, at the microscopic level, they provide some interesting insight. And I'm gonna discuss about a natural lifting that appears that is the kinetic lifting. So most of the success of machine learning can be, well, maybe I'm exaggerating, but can be attributed to the idea of this high-dimensional space when the problems become easier. So,
Tonio, before we go into depth, can you define for us what do you mean by non-locality? Because the different things mean to different things to different people.
So
non-locality for you here in this.
So every aspect of space-time is gonna, well, every aspect of space is gonna be interact when we are applying this operator.
So are you thinking of non-Markovian system, for example?
And this problem, I'm not sure this analogy holds, but I'm talking about like you system change the entire, so you move the entire space in this problem. So for instance, what I mean is that you have a space X T, all the aspects of X are going to appear here when we are moving it. This is what I'm mentioning here.
Okay, that's not what non-locality means mathematically. For example, you have a discontinuity that induces non-locality.
Okay.
Because singularities induce non-locality. So, but that's not what you mean.
Yeah, what I mean in this case is the fact that we are not using like an integral operator. So everything is going to be like point-wise in this framework. This
let's see.
Locality, and the non-locality is not going to be in this framework. Okay, so I want to mention about this kinetic lifting, and some analogy that we can, at least to me, has been very helpful, is to understand, and this in the formal level, as in machine learning, like first course machine learning, we see that we have to circle, and this cannot be separated, linearly separated. But if we increase the degrees of freedom, we lift into a high dimensional space, so we can have a circle around here and a circle here, and we could put a hyperplane linearly separate those. So it's something similar what I mentioned here. We go to a higher dimensional space when the things becomes easier. Another aspect when I mentioned this kinetic model, that now rather than working directly into the observable, we are talking about the distribution functions. And this distribution function, that we are considering a kinetic framework, they follow a very simple scheme that comes by transport and collision scheme. The nonlinearity of the system is going to be decoupled from what I mentioned here, the non-locality of the system that so I mentioned that acts in the whole space. It's going to be decoupled by a nonlinear operator that becomes the equilibrium state. And this is mapping observables to the equilibrium. The other aspect of the whole field, field is interacting is going to be linearized, and this becomes a linear transport operator. So if you consider this operation, this is simple to solve. This is nonlinear, and something that to consider that this nonlinearity make it interesting for the use of machine learning. We in this work we propose a neural network to map microscopic observables to equilibrium states. So I'm going to be more specific about what we are considering. So we have these microscopic these observables. So for our case, we can consider the hyperbolic system like this, or we can consider it's okay to do it. Though the theory that we are mainly taking into consideration comes from this paper from 1999, is to have a dissipation is okay. And at this context, we can still deal with that. But if we try to keep follow exactly this paper, this equation can be lifted into the kinetic framework. And with this kinetic framework, we have a very simple collision that is the BGK collision. So you pay attention to this equation on top. This is a linear transport. This is linear. This is simple to do. So the whole aspect that make it complicated in this regard is going to be the equilibrium state. And the input of the conservation law is going to be part of the equilibrium, but only depends on the velocities of the system. So let's make a mental image that we have an oracle that is able to provide to us the equilibrium state. So this part is relatively easy when we have that oracle. And this part is also very easy. So we are paying a price that going to more degrees of freedom, because rather than working in space-time, we are working in phase space, so we need to add these extra degrees of freedom. But the question now is a semi-linear hyperbolic system, or you can consider that this becomes a nonlinear source. It depends how you consider. Is there any questions so far? Okay, if not, I will continue. Now, with this point of view, the F is theoretically is a vector value particle density defined on phase space. We can consider what the equilibrium is if we go to the Chapman-Enskog analysis. But there exists a very axiomatic point of view of seeing the equilibrium state. And given that we are at this level and we need to keep track of this equation, so you may ask, how do we recover the observables? And the way to do it, and I actually highly recommend to read this paper, is by taking projection onto some moment bases. These moment bases are going to be polynomial of the velocity. When you project the distribution with respect to this polynomial, you can approximate some the observables. Therefore, these questions are very complicated for us to consider, and not mean that we cannot consider, but this is significantly simple. At least we have the advantage of this linear transport. Now, another aspect I want to emphasize is that given that we are in a kinetic framework, we can use an spinning operator technique. And for that, I'm going to present a cartoon or something that helped me to make a mental image of what's going on. And if we assume that this square is very, very small, like size of the mean free path, and the time is the corresponding time corresponding the small scale that we observe the molecule. These molecules follow a ballistic in that very short period before they collide and they make an interchange. So that makes a very natural perspective. We can alternate between collision and transport. And this make a very powerful point of view. The whole perspective now is simplified. Now, of course, we have to pay the price of higher dimension. And to this point, I want to give another good perspective of how the probability distribution actually appears. And let's suppose that we consider a flow, and we zoom in into this flow until we are able to see these molecules. So the probability distribution that I'm mentioning here, at least mentally, can appear if you consider in this this very small volume. We consider all the velocities that go into this direction. You count it and you divide it into the amount of molecules. Of course, this is just a mathematical perspective. You have this point, and you continue, and you're gonna have a density here. The evolution of that density is what is gonna give you this equation over here. But we are not interested in that evolution. At least we are interested in solving the microscopic point of view. Therefore, we can remove almost all the velocities in this microscopic point of view, and we just keep track of few of them. Given we are interested in observables, and these observables is going to appear by some polynomial with respect to the velocities, we need only to keep track of those. So we have a polynomial here, and we have an integration. We can use a quadrature rule to interchange the Lebesgue measure into a discrete measure. And therefore, now our phase space corresponds to time, space, and a discrete velocity that is much, much smaller than consider the whole non-negative RD times RD. So now our space is still more degree of freedom than original space, but it's shrink, given that we only need to keep track of the observables of the system. So the whole idea of what's going on, it can be summarized in this cartoon diagram. So we are interested at this bottom, this conservation law, or you can consider some dissipation if you want, this is also possible. And in order to do it, we listed, speaking the language and much of the people in machine learning are familiar with, into a high dimensional probability distribution when we have this simple collision transport, and we are able to evolve that probability distribution. And if we need to probe the system to see what's the microscopic observable, we can do it by projecting back, and that given by moments. Of course, this top is the ideal case. We can simplify that top part by finitely many velocities. And the only aspect that is going to be unknown is going to be the equilibrium state. And let me be specific why, because I am very sure that some of you may have this question. If we go to this top and let's consider that we are talking about gas dynamics, we know the equilibrium state is going to be the Maxwell-Boltzmann distribution. But this comes from extremizing a principle like the kinetic entropy. When we discretize that system, we have finally many velocities. So the solution is no longer the same because we need to discretize the principle, and we need to discretize the velocity, and after that we need to extremize, and that is going to give you the corresponding equilibrium state with discrete velocities. So this middle section is what we are considering in this paper. Is there any questions so far? Okay.
I mean,
So
Antonio, this is very similar to also what we do in DSMC, direct simulation Monte Carlo.
Yeah. In direct simulation Monte Carlo, yes.
Split and so on. Yeah. Okay.
Yes. Yeah, actually, in direct simulation Monte Carlo, you have the micromolecules and you have this evolution, right? And the collision is a random process. If I remember, you take it.
That's
Yes,
correct.
very
That's
similar.
correct. Yeah.
Yes. It's very similar.
So, sorry, I want to ask one question. Zerks here.
Yes.
The point here is that you're going to try to define just the equilibrium with the neural network, and that's going to help you resolve the conservation law. Is that the idea?
Yeah, that's a spoiler, but yes, that's the idea. Yes.
Okay, thank you.
So I'm gonna mention here is why I consider this very interesting. I'm very sure people here are more knowledgeable about this idea. I can give a higher list. But what I consider very interesting is that this problem, we don't need to solve this local Riemann. You don't need these local Riemann solvers. The advection is linearized. We can even simplify even further the velocity space. In order to do it, we can consider like a further structure, like a lattice structure. So lattice structure, you can consider this is a pk. The velocity is gonna be a constant multiplied by this simplified velocity that comes from an integer. And when we have this lattice velocity, the transport becomes a shift operator. And you want to see in numerical application, the shift operator is basically a change on memory, and they have non-numerical dissipation. We avoid the convective derivative, and in order to consider to have access to the microscopic fluxes, we can just get access to them by taking a statistical moment of the distribution. Okay. So I'm gonna focus now in the main point of this work is gonna be the equilibrium state. As I mentioned before, the equilibrium state, how it actually is gonna appear, it's gonna appears like a you are a physicist or mathematician, you can consider minimization, maximization. So I'm gonna be general and say that we are extremizing a kinetic entropy constrained to some moments. This moment is gonna appear like some conservation laws. So in the paper that comes 1996 from Livermore, and their follow-up from this paper of Talek from 1997, they prove that the formal solution of this optimization problem has this form. So you have an exponential, you have the basis of the velocities, and here you're gonna have the Lagrange multipliers. So something to keep in mind here is, even though the equation 1 looks simple, in order to resolve it, we need to use a root finding algorithm. And this root finding algorithm needs to apply for any point in time and any point in space. So we are talking about like a three-dimensional flow. This is very expensive. And to accelerate that process, I think it's very natural to think into the problem 1, like considering some neural network like a basis of the moment. And we can amortize even further by another network around here. And this is exactly what we did in this paper. So we use the formal resolution of this extremization of the kinetic entropy, and we replace the basis and the corresponding Lagrange multiplier by a network. And I think I don't need to specify for people in this audience, but if you look very carefully, this is exactly the form that appears in DeepOSets, right? The only difference is that we have this renormalization map that comes from the extremizing the kinetic entropy that you see around here. So this is gonna be, if I remember correctly, this is gonna be the trunk. The bases are the branch, if I remember. Please correct me if I'm wrong. But these are gonna be our surrogate.
The base is the trunk.
Equilibrium.
I mean, you have the basis correct. You have it correct, but the base is the trunk.
The
Pk
base
is the basis.
Okay, so these are the trunk, right? The bases and the combination is the branch, right?
The coefficients, the function is the input, yeah, which is the time dependent. Yeah, that's right. Yeah.
Yeah. Okay. Thank you. So some question I have, maybe if people here interested, I like the connection that from this paper from 1996 to what is currently some of the main architecture and operator network. So for people in this audience, maybe you may ask if we can consider the DeepOSets like a maximization of some kinetic entropy given some conservation. But okay, I'm gonna follow up. Okay, so far we have the surrogate of the equilibrium state. Good. We still need to solve the evolution given by a linear transport part. So in order to do so, we can either use a discrete velocity model, or given that we try really to some kind of microscopic level, we can even simplify it further. And we are gonna keep velocities in the lattice, and this immediately is common to the Lattice-Boltzmann community. So this is what they are doing. The main difference is in the Lattice-Boltzmann community, most of them, they have this expansion of the Boltzmann distribution in terms of their mid polynomial, and that forms the equilibrium. For us, this equilibrium is going to be a surrogate by the NA network. And everything else is not going to be learnable. And I want to give some, at least some formal analogy that I like with this procedure, because I know that most machine learning will try to learn the whole process. But an algorithm I personally like it is the score-based diffusion model. And I like this analogy. I mean, it's probably a formal level, but in the score-based diffusion model, you have a model that is the only aspect you learn from this model is the score when you need to do the reverse by the reverse time stochastic differential equation. Everything else is not learnable. So in analogy to that, our procedure, we are fixing the, you have the lifting given by the kinetic and modeling. We are not learning outside of equilibrium state. So the whole machine learning in score-based diffusion is going to be learning the score. In our case, it's just the kinetic entropy, the kinetic equilibrium. And the rest is going to be addressed by traditional methods. And you want to see that actually Lattice-Boltzmann is able to solve some of the hyperbolic system. I highly recommend this paper. It's in JCP for 2014. And an aspect I want to mention is that given that we have a very physical spire, we want to see that the null network is pretty small. Is there any question to that? Okay. So given that we have this Lattice-Boltzmann for the transport term, our algorithm in the most simplified form is going to look like this. So this is the aspect that's going to be learned, and everything else is very simple once we have this oracle that provide equilibrium state. For some of the experiment, we actually consider two population distribution, and one of the reasons is presented in this paper, but in the most simple essence is equation 3. And we are considered the equilibrium, the population is just discretized in terms of velocities in the lattice. We consider a dimensionless Lattice-Boltzmann method, where the equilibrium state is provided by the nano.
So here you're using the multi-relaxation model, right? That's the idea? So you have
in this one, yes, because in some of the experiments,
tau 1,
we are
tau
gonna,
2. Yeah, to get the
the specific fit ratio and that number. Yes.
So,
yes,
but
yes.
tau 1 and tau 2 and so on, they're multi-relaxation factors, different penalties.
Yes.
Okay.
It's gonna provide a prime number. So in this case, for some of the compressive flow that we have in the experiment, yes. But in the most simple essence, our numerical scheme is gonna look like 3.
Could I ask where did the velocity go for phase space? I just missed that. That's integrated out when you move to the Lattice-Boltzmann?
Yeah, and the Lattice-Boltzmann is gonna be the lattice structure, yes. That's this velocity. Because the velocities in at least what make it very, you can generalize Lattice-Boltzmann method, but what make it very simple is when you have the lattice structure in the Lattice-Boltzmann method, because that extremely simplified the advection part. without any numerical, we don't need to do anything rather than rearrange the memory. So this is very efficient.
Okay.
Okay, so our algorithm is a hybrid algorithm, and basically separated and we initialize the population, this population of the distribution. We get our equilibrium state, and in order to get our equilibrium state, we need to map to microscopic, and we use our surrogate neural network that map microscopic to equilibrium state, and this is what is split around here, the equilibrium state. After that, that equilibrium state is used in our splitting algorithm that is divided in collide and stream. And as you see, the streaming, given that these are, these things are just shift in memory. So this aspect has no numerical dissipation. And we can accumulate and we can accumulate for part of the training, but in essence, the algorithm looks like this. I already speak about this, but it's probably good to mention it briefly. So this is what we are interested, microscopic level. We can lift that microscopic level into a mesoscopic level. We can train our neural network with the lattice Boltzmann, and our testing is going to be at the mesoscopic level. And we are interested in knowing what is the observables. We can always probe that by the statistical, by taking projection. Okay, so I'm going to be probably brief here about the training because I want to jump quickly to the experiments. So for the training, something I want to mention is we use a two-step training. And one of the reasons make very, because this part is a little bit unstable if we don't consider the first point. We pre-train the architecture like a standalone model, because at the end the model is just, you feed the microscopic and you split the equilibrium state. So we train it like a supervised learning, and that helped for the second section when we integrate the architecture into a lattice Boltzmann method, and we use what most people in machine learning for fluid dynamics are doing, that is this idea of rollout that is presented here. This parameter of the rollout, we know that it can be significantly increased when we pre-train the neural network in that form. But the whole point is that we have this algorithm, we provide the equilibrium and the prediction of the distribution, and we can penalize to improve our result in our training. Now I'm going to start with the numerical experiment. So something I want to emphasize is that the neural networks that we are able to get are, I think, are relatively small for the alpha and the basis, the phi, and we consider three cases: subsonic case, near sonic case, and a supersonic case. And this one is 2D. These are 1D. In all of them, we consider the yellow activation function. And for all of them, we use the same renormalization map that comes from the exponentiation. Okay. Then these are the velocities, so that you can observe. So you have here particle, and you have the line velocity that we use. So for the audience that have experience with lattice Boltzmann method, one of the main issues of lattice Boltzmann method is when the flow is near sonic, and we need to increase considerable the number of velocities, or we need to be more clear with equilibrium state. So in this case, we are going to be very small in terms of the velocity. Two neural networks are relatively small. And for all the cases, the algorithm that we use continue autoregressive manner until either we finish the simulation or a numerical instability appears. And if it is possible to see if the neural network actually is doing something more than a traditional lattice Boltzmann, we compare with the polynomial expansion of the lattice Boltzmann method. As I mentioned before, this polynomial expansion comes from the Hermite polynomial. Okay, so this is our first case. So the stark shock tube. So we have two different pressure, a high and low pressure. And this is a benchmark for fully compressible flows. And we have three nonlinear waves up here. There are refraction wave, contact discontinuity, and a shock wave. So if I don't mistake it, a refraction wave go in this, and the contact discontinuity and shock is going to be in this direction. If I'm wrong, I'm happy to correct me because I'm not an expert in fluid dynamics. So we have these two cases. These are in order to change the adiabatic exponent, we add the dynamic viscosity. So this case is much simpler than this case, and the difference in pressure is 10 times here. And this is our simulation. So this is the case one. In the case one, we have subsonic case, and we are able to actually compare the result with the polynomial equilibrium that is traditionally used in Lara-Boltzmann, and we see that the polynomial equilibrium, that you can see this small, like very thin line, they generate some spikes here that correspond to this section, and here. When the reference that comes from actually solving the equilibrium state by a Newton method and the neural network, they actually don't have it, and they actually follow each other. So what I want to mention about the training, we just use for the training the first 500 time step, and after that, we remove the training and we make an inference 500 time step. And you see 500, 700, and 999. And you see that there's a slightly difference between the equilibrium coming from the polynomial and the equilibrium coming from the Newton's method, but the neural network and our reference actually follow very well each other. Just for the audience, this is a much simple case. This is still a subsonic case. And the second case is actually near sonic. So this case is more complicated, and we unfortunately couldn't simulate the polynomial because it immediately blows up. So that's why you don't see it in these plots. The simulation of our surrogate and the reference, they follow well each other for at least the 500 time step. There are some small differences along here, and maybe if we really try to pay attention, we can find some of the artifacts like here. But I think for an autoregressive model, give you 500 times step is very, very good considering the size of the network. And this case is actually near sonic. And this is very complicated for Lara-Boltzmann method. So actually our network is doing what it's supposed to do, that is learn the equilibrium state.
I have a question. Have you tried to, in here, have you tried to do larger pressure ratios here? The largest it was 10, I think, what you had.
Yes, it's 10. Yes.
Because we had a paper, I think Ahmed can put it on the chat, called Riemann net. We went to pressure left over pressure right to 10 billion. 10 billion.
Okay.
So that's a tough problem. Maybe you can look into it.
Yeah. Yes, definitely.
I don't know if you know the paper Riemann net, because it's all about Riemann net. It's all about neural operators for very. I think Ahmed put it on the chat, so you can take a look at it later. But it's very, very similar for different neural operators. We compare different neural operators, but for extreme cases, not these are very mild cases actually.
Okay.
Yeah, it's good that it works. It's just that.
Yes, I'm happy to look into the paper. Thank you for the reference.
I want to make sure I understand the motivation of this here again. These simulations are all equilibrium fluids, right? Like just an Euler solver will pick this up. Is that fair, or are you non-equilibrium, like non-Maxwellian fluid?
For this case, I mean, you can do it, definitely, but in this talk, we are considered use this lifting high dimensional for solution of this kind of equations. So you are totally right that we can do it with like an Euler solver, but we are trying to do a high dimensional point of view for this kind of equation. And now we are considered only the Euler equation, but we are trying to go into different kind of conservations, as this form is very general provided by this paper.
Sure. So the ultimate goal is to look at
Different, yes.
different kind of closure models and see if you can model them more.
Yes, yes, yes.
Actually, one further question. When you said you were doing you were looking at Hermite polynomials, there the equilibrium is defined, is that right? Like, what did you mean by that? Like you compute the coefficients from.
You mean for this? Yes, you expand so the equilibrium in this problem is going to be the Maxwell-Boltzmann distribution, and you expand it by you have a polynomial expansion given by the Hermite polynomial. This is most of the IBM community are doing. And this works very well, but very weakly compressible flows. But when you use,
Like, I mean, you could also just drop the trunk net and then just use the polynomial expansion and learn coefficients. Did you look at that?
you trunk that. I mean, let me see if I understand. So you mean this replaced by polynomial?
Oh,
I
I
just
guess
learned this configuration.
okay. So, okay, when you say Hermite polynomials, you're approximating two with a series of Hermite polynomials. Is that?
For the polynomial version of this, let me see, for this simulation, yes. So basically what you have is you expand the Maxwell-Boltzmann distribution in terms of Hermite polynomial, and you use that like as equilibrium state. And this is the most common way to do it in the Lattice-Boltzmann literature.
Yeah. So we did something for particle and cell, more DSMC non-equilibrium flows, where we did Hermite expansion around the BGK operator, and we're able to get non-equilibrium dynamics, at least in the kinetics space. But it seems very conceptually similar. And so I think you might be interested in looking at that. So thank you.
Yeah, sure. Yeah. I mean, would you mind to put the paper in the chat so I
Yes,
can look at it?
of course.
I do
Yeah.
appreciate it. Thank you. Okay. So something we found when we try to do this autoregressive model for getting the evolution, found that at some part we have certain oscillations. So we have this paper for machine learning, but this is very old method that in order to avoid some oscillation, at least for the first order, we use a TV like a regularizer. And it works very, very well for this problem. Now, you may ask what happens if we go to a multi-dimension. So this has actually kept my mind that this paper from Livermore, I personally like this dissipation part of the collision operator that give, in essence, the Boltzmann-Edge theorem that can be used like a regularizer in order to avoid some of the issues of the oscillation. But for the purpose of this work, this worked very well. This is what we see when we are trying to make the simulation. We see that the regularizer works really well to remove all the oscillations. Okay, so I'm almost finished. So I'm going to talk now onto the 2D supersonic flow that we consider. So in this case, we go to very small Reynolds number, 300, but we are going to be the supersonic regime. My understanding, but I cannot open that box for you, is that this is useful for the aerospace industry for the dynamics of aluminum particle for solid rocket motors. So it comes from this paper for Nagata, but the simulation is very inspired by this paper from LAT in 2020 for the Lattice-Boltzmann community. And we have the same setting. We train by a few time steps, and we find the equilibrium state, and we follow the Lattice-Boltzmann for the rest of the simulation. The boundary conditions are presented here. The normal boundary condition is delay and free streaming. And after one point, we follow the dynamics and see how our simulation with the Lattice-Boltzmann and their non-network equilibrium compares against the simulation. And even though it's not perfect, we found like a little bit of artifact here compared with the numerical simulation. For 500 time step, I think is and given that we are this is a Mach number, close to Mach 2, this a very it's a complicated problem. Of course, we can increase the Reynolds number and make it more complicated, but the Post-shock is well resolving this problem. Now, so far I'm saying,
is the flow steady here?
at the beginning, no, right? Yeah, after a while, yes, it gets steady, right? By the Reynolds number.
Why is it steady?
The Reynolds number is very small, right?
No, the Reynolds number, even 50 for incompressive flows, gives you unsteadiness. For compressible, it's not clear, but it is. It depends on the Mach number, perhaps. But so, but you're carrying out an unsteady, right? You consider the unsteady part, and then you converge to this.
Yes. So you train the steady part, and after that, you use the numerical simulation for
What's your reference to the right? How did you get the reference? OpenFOAM, or what did you do?
No, let me go. So we keep the. Oh well, actually I have it here.
No, just the reference. You compare.
Yes, we use the. So we use again the Lattice-Boltzmann method, and the equilibrium state was implemented by root finding algorithm.
I see. So you're comparing against another Lattice-Boltzmann, the direct vanilla Lattice-Boltzmann. Okay.
Yeah, not vanilla Lattice-Boltzmann, because the equilibrium state, the vanilla Lattice-Boltzmann cannot handle Mach 2. So we compare it with the equilibrium state solved by root finding. So we also said the equilibrium state like a paper level moment that is in this exponential form, and we get the coefficients given by the Newton method at each point in time and space.
Okay, thank you.
So far, what I'm mentioning is interesting. We can train some power, and the non-network is able to find this equilibrium and have a prediction that go to 500 times step in compressible flows. A much interesting point of view, I think for me is okay. We train here, and what I presented is this inference in this 500 times step. So what happens if we keep evolving the flow? We use the initial condition at this point, and we try the non-network with the train equilibrium to predict the next 100 times step. And this is what we do here. So we present some of the reference of the flow, what the non-network saw. The last one was this 499, and we keep evolving the case one, that is a subsonic case, and we take the initial condition at time 2000, and we evolve the 100 times step with the non-network, and we see if the network is able to get a good match with our reference that comes again for this Newton method. For this case, there's a small artifact around here, but it follow the reference solution. And we did exactly the same for the second case. We train it 500 times step as before. We pick the time 2000 for our initial condition, and we follow the prediction of non-network against our reference for the next step. And there's a small artifact here. There's a small discrepancy here and here, that the simulation match our reference, except small changes in the boundary conditions. And for the chaos cylinder, what we do, given that go to a steady state, is we retrain, but rather than use 500 times step, we reduce to 150. So we only use 150. We use the same architecture, same procedure. So we only train at 150. we let the flow evolve all these times, and we predict what's with the initial condition, this initial condition, what is the next 500 time step. So this is the last simulation that the non-network was able to see, and this is our non-network against our reference simulation. But of course, not everything is.
Can you clarify when you say flow evolution, during that period you're using the CFD solver?
Yeah, solver. So we see the evolution of the flow by the solver. Yes.
Okay. So how much of a speed up you will get here? Because I suppose the only reason you do that is to get a speed up, right? You interleaving the neural operator with the CFD solver. But do you get a speed up?
For this particular case, actually, I mean that's a good point, and I think that's something I've been in my mind to.
Well, that's not a good point. That's the only point. The only point you would do that is to have a speed up, because the accuracy, you're not going to compete with the accuracy.
The point I want to make here in the prediction is I want to see if the non-network is actually really learning the equilibrium state correctly. So that's why we left some. Here in the train and inference, maybe the shocks are too close together. That is just following out the evolution. If we left the evolution of the flow, we at least this experiment we want to see if the non-network is actually capable of understanding what's going on. That's
because we did very similar things with the materials microstructure evolution, and they use Memphis versus as a solver versus neural operator, and you really need to work hard to get a speed up. But we demonstrate speed ups of the order of 60, 50, and so on. But here I doubt it that you have a speed up. Certainly for the 1D, you not. You have to go to high 3D to get a speed up. But this is interleaving. It's sort of, that's a thing that we want to do, to interleave the CFD solver with the inference and take a big step forward. But you at the end, you need to have a speed up. Otherwise, you just use your solver.
Yeah. So actually, the follow-up we consider a 3D case.
But also,
well, actually, it's very expensive.
You probably that's why I asked about the steadiness. You probably need to have. You can go to low Mach number. In which case, if you go Mach number 0.8, for example, this is an unsteady flow, a periodic flow. You have the vortex street, even at this Reynolds number. So then it's better to have an unsteady flow to show that as opposed to steady state, because when you get to steady state, you stop. So it's only through the transient that you can interleave.
So the point, at least for the Lattice Boltzmann community, is that if we go with low Mach number, the equilibrium state provided by the mid polynomial are actually accurate enough for the simulation. So the problem actually starts when we go to Mach 1. This is when the Lattice Boltzmann is.
Then you can move the inflow. You can make you can put a sinusoidal component in the inflow velocity.
Okay.
So it doesn't have to be steady.
Yeah, sure.
For steady problem, you're not going to win. So it's really meaningless.
Okay. So just to wrap, we continue this experiment to see when we can break apart the non-network, and we find that again the non-network is only trained at 400 time step. We find that around 4,000 is when the non-network significantly diverges from the reference simulation. And in the second case, that we are in the near sonic, we have like the oscillation start appearing. And that's end my talk. Is there any further question? I'm happy to answer any.
Do you have any questions from the audience? Maybe I have a question.
Yeah, sure. Please.
Hey, can you go to the previous slide?
Mhm.
To the one where you had like this that one, yeah. So in here, what you're doing is like you're training the first 150. You're using that for training, and then you're using from 900 to 1000 to testing, right? So it's just so if right, that's if I got it right, like you're using from the first 150 time steps to train, and then you're evaluating your model from 900 to 1000, right?
Yes, yes. It's the same here. In this case, we train on 900, 500, and some of the simulation you saw previously is from 500 to 1000. But we keep evolving the solution using the largest volume with the root finding by the Newton method, and after that we test from 2000 to 100 times. That's to see the prediction without
Yeah.
in this aspect without any training at all.
Then that brings to my question. Did you compare the relative L2 error or some kind of error metric when you put the inference right after the training and when you put it way after, like to see how the model behaves?
For this, how that just compare? Yes, I don't have it in
Like
this
for
slide.
example, when you compare this part, let's say what is
Mhm.
the relative error here, and
Mhm.
the comparison with the relative error here. So in other words, would be how well the model does when it's farther from the training data. You may have some performance degradation, right? But how big is that that degradation?
Yeah, actually, that's a very good point. I don't think I have this experiment, but that's something I'm definitely gonna consider. Yes.
Oh, okay.
Yeah, thank you.
Do we have any other questions from the audience? Maybe not. So I think that we can go start with the next speaker. So thank you so much, Antonio, for your presentation. This was a really good talk.
Thank you for inviting me. Let me stop sharing my screen.
Yeah.
And thank you for all your comments and your discussion. I appreciate it. And thank you again for the papers. I'm gonna read them.
Thank you, Antonio.
Our second speaker is Professor Ulisses Braga Neto. He received his PhD in electrical and computer engineering from the Johns Hopkins University in 2002. He's currently a professor in the electrical and computer engineering department at Texas A&M University. His research focuses on machine learning and statistical signal processing. Dr. Braga Neto is the founding director of the Scientific Machine Learning Lab at the Texas A&M Institute of Data Science. Damn it. He has published 2 textbooks and more than 160 peer-reviewed journal articles and conference papers. Dr. Braga Neto received the NSF Career Award in 2009. Professor Braga Neto, thank you so much for joining us today. We are all looking forward to your talk, and with this short introduction, you can begin.
Thank you, Juan. That was a nice introduction. Thank you. Is George on the call as well?
Yeah, he's here.
Oh, hi,
Hi,
George.
Ulisses. Welcome.
Nice to see you again. So, thank you for having me back here. The first time I was giving this talk was, I think, 4 years ago. So it was different time, but so thank you again for inviting me, and I'm happy to present this work. It's a collaboration with my PhD student Steven Chiu and Jun Yuan Hong from UT Austin. So let's begin. So what we're going to talk about is the convergence of three things. It's in context learning, operator learning, and permutation invariance biases. So we need to talk about each of these 3 things, okay? So let's start with permutation invariance biases. So suppose that you have a function which is a set function. Okay, so it basically, in this case, it counts the number of elements in a set. So for instance, you've seen some examples of this function. Now, this function, you can see that it's invariant to permutation of the elements of the set. So I can reorder the elements. It doesn't change the value of the function. And also, it applies to sets of any size. So these are the two main features of a set function. It's permutation invariance and applies to sets of any size. So we can try to use a machine learning model to learn such a set function, okay? So if you give me input and output pairs, I can try to learn this function. But this machine learning model has to accept inputs of any size. And plus, it would be advantageous for us to add a permutation invariance bias, because we don't want our machine learning model to have to learn that it's permutation invariant, right? That would require much more data and a much bigger model. So, so we want to add this permutation invariance bias directly into the architecture. So this is an example of set learning, okay? And this is becoming, very widespread now and popular. So in our, let me move here now. So, in a large part of the talk, we are going to be talking about the regression problem, the supervised learning problem. So in this case, you have a data space and you have a hypothesis space. So, your operator maps from data to a function. So notice that this is not like just a regression function that maps from, a point in the space to a value. No, this operator maps from, the data to a function, okay? So it's a mapping between, in this case, a finite dimensional space and an infinite dimensional space. So, but notice that this is a set operator because the data can be reordered, and typically your regression will not change if you reorder the data, okay? And then, of course, the data can be of any size. You don't know a priori what is the size of the data. So if you have an algorithm that performs regression, it has to work on data of any size, right? So this is a set operator, okay? And learning this operator is a set operator learning problem. It's an operator learning problem, but in this case, it's a set operator learning problem. So DeepOSets is a machine learning model that can learn these set operators, okay? So it accepts inputs of any size, and it has a permutation invariance bias. But in addition, it is an efficient non-autoregressive architecture because most, if not all, approaches for in-context learning out there are based on transformers. And we haven't talked about in-context learning yet. We will in a second. But DeepOSets can perform permutation invariant operator learning through in-context learning. And in fact, it is a non-transformer approach for that. So okay, so let's define a permutation invariant set operator more formally, okay? In this case here, we're gonna fix the input size just for technical reasons, okay? But let's assume that you have a data set of a certain size, n, and you have an operator that maps it to the hypothesis space. So the operator, of course, is permutation invariant if you have a permutation, okay, and you can apply that permutation and it doesn't change the value of the operator, okay? And then we say that an operator is continuously sum decomposable through a certain latent space Z if there's a continuous function from each data point to the latent space, and then a continuous operator that takes you from that latent space to the hypothesis space. So, you know, it's an operator between a latent space is typically, not typically, but always of finite dimension. But of course, the hypothesis space is infinite dimensional. So you have an operator that takes you from the latent space to the hypothesis space. So, and if you can write a decomposition like this, okay. So if there is such a decomposition, then we say that the operator is continuously sum decomposable. Okay. All right. So there is a representation theorem, which is an extension of. Let me try to get rid of this window here. That is okay. That's fine. So let me go back. So there's a representation theorem that says that, you know, a continuous operator of this kind is permutation invariant if and only if it's continuously sum decomposable through Rn plus 1, okay? So you know, if you don't mind, I'm going to stop sharing for stop the presentation for a second, okay? Now I'm going to resume because there was a window in front. Okay. Sorry about that.
Ulisses, it was fine for us.
Yeah, it was fine for you, but not for me. I couldn't see part of the slide. But okay, sorry. So now it's okay. Now it's okay. So it is permutation invariant if and only if it's continuously sum decomposable through Rn plus 1. So the latent space has to be of size at least n plus 1. Okay, in fact. So this is an extension of a result for set permutation invariant functions. Sorry, set functions, permutation invariant set functions. This is an extension for permutation invariant set operators, or you know, operators. So this is proved in the paper. Okay, in other words, you can always write, you know, such an operator in this form, where you have a continuous function phi from each data point to the latent space, and then you have an operator between the latent space and the hypothesis space. So this corresponds to an architecture like this, okay? And now this is going to be the inspiration for proposing DeepOSets, okay? Because we can replace this phi by a neural network, and we can replace this gamma by a neural operator. And that's the basic idea. And then the pooling, which here is summation, can be also more general than summation, okay? So let's see. Now, before we can do that, we have to talk about the operator network that we're going to use. So we could use different operator networks, but we're going to use DeepOSets because it has an universal approximation guarantee, which we're going to use. And also, it does not discretize the output, which is a big advantage. So we only discretize the input to the branch network, but it can evaluate the function, the output function, continuously at any point through the trunk net. And I believe that this is a big advantage over other operator networks. So, all right, so with that said, now we move to in-context learning, okay? So for in-context learning, before we talk about the general architecture, DeepOSets, let me just introduce briefly in-context learning. So the idea is that this is an increasingly popular form of machine learning now, where you have a trained neural network that learns from examples and a query provided by user prompt. This happens without further training. So, once the model is trained, you give a few examples and a prompt, and the model learns the correct response without further training. So, for instance, in natural language processing, this is a well-known phenomenon. You can use ChatGPT to do in-context learning. So, what does that mean? So, suppose that you want to predict whether, so we're gonna do sentiment analysis. So you want to predict whether a restaurant review is positive or negative. So in the prompt, you're gonna give a few reviews and whether it's positive or negative, okay? And then you give a query, it's a new review, and then the model is gonna predict whether it's negative or positive without any further training. It's not trained again, right? So this is a phenomenon that was observed, and it's called in-context learning for these large language models. But our task is numerical, okay? So for our task, our examples will be data points with input and output. So X and Y. So each data point consists of a point in the space and the target value. And then you have n examples, right? And then a query is a new point in the space, and you want to predict its value. Okay? So this is our prompt. So at inference time, so you're going to train, of course, the model on these prompts with the value of the query, and then at test time you come with a new prompt and you don't have the value of the query, so you have to predict that. Okay. So like I said at the beginning, this has been done using transformers. Because why? Because that's what they use in natural language processing, and that's how it was observed. The phenomenon of in-context learning was using transformers, okay? And transformers can, of course, accept inputs of any length, and they can be made also permutation-invariant by hacking. So, removing the position encoding that they use in natural language processing. So basically, seems to be a natural thing to do, except that transformers, these kind of transformers that they use, are autoregressive, which means that you have to process the prompt sequentially, okay? So you have to give the first X and predict the first Y. Then you give the second X, predict the next Y, okay? So you have to process the prompt every time. You have to process the prompt sequentially. If you change the query, you have to process the prompt again. Okay, so that's how transformers work. And then obviously transformers have a complexity because of the the inner product self-attention, dot product self-attention. It has a complexity n squared. So every time that you process the prompt, so the complexity is n squared, where n is the number of examples in the prompt. Okay. So but this was used probably for the first time in 2022 for these numerical tasks. Okay. They were supposedly doing that to investigate this phenomenon of in-context learning and they were using simple numerical tasks to do that. Our objective is more ambitious than that. We want to really use this to do realistic operator learning, okay? And obviously, this is we have some preliminary results in that direction using simple examples, as I'm going to show you. But we're going to have examples that show, of course, not just regression, but also automatic or multiple operator learning. So multiple operator learning for both regression and PDE operators. So regression operators and PDE operators. And the goal, like I said, the ultimate goal is to make this into a realistic tool, okay? And I'm going to show you preliminary results for that. Okay, so like I said, the main disadvantage of such approaches is very high complexity, okay? You have to use very large transformers to do very simple tasks, okay? So for instance, for this kind of regression tasks, admittedly, not just one dimension, but they go from up to 20 dimensions, but this is still a linear regression, so regression with a hyperplane. They are using a model with 9.5 million weights, right? 12 layers of 8 attention heads with a 256-dimensional embedding space. So it's fairly heavy models for such simple tasks, okay? So our goal is to see, okay, one of the experiments we did is to compare DeepOSets to this kind of architecture and see if we can do the same thing, but with a much smaller model. And plus, processing the prompt in parallel. So we don't have this sequential processing of the prompt. Okay, finally, here's the architecture, okay? We use the representation theorem, and then it's inspired by that representation theorem. So we're gonna have an encoder into the latent space, here. So the encoder is essentially a DeepOSets architecture. So we're gonna have, each of our examples in the prompt goes through a linear layer to embed in a higher dimension space, then it goes to an MLP, and then each of these points are pooled, and that makes it permutation invariant, right? This pooling operation is permutation invariant. And this can be applicable, once it's trained, it can be applicable to any size of prompt, because all the data points go through the same linear layer, the same MLP layer. So it can be applicable to any number of points. And then, obviously, then, from once you have the latent representation, then that goes into the branch of the DeepONet, and then you evaluate the output function on using the trunk, okay? So it's the same idea of DeepONets, but the input to the branch there's a permutation invariance bias, which is produced by the DeepOSets. If anybody has any questions, okay, you can stop me and ask that. Yes.
Hi, this is Kamal from Brown. What is the size of edge to the branch?
Yes. So the representation theorem says it has to be at least n+1. Okay, but in practice you can use a larger number, to facilitate training. But to obtain such decomposition, it must be at least n+1, which is n is the number of examples. Okay.
So
Since
the
you don't
pooling
know
is
up
basically
beforehand, yes. So go ahead.
the pooling is like what we do in CNN, like the average pooling or max pooling.
No, the pooling is like, for instance, a sum. So the input are vectors. Okay. So h1 ... hn, these are vectors.
Yes.
And then the pooling, you for instance, you're summing the vectors. Or you could also take the maximum component-wise,
Okay.
of these vectors. So it's a summarization operation, which is permutation invariant. It has to be permutation invariant. In the representation theorem is the sum, but here we can use other things. Okay, so we can use other kinds of pooling. Okay, so it's not the same as in C.
CNN.
Okay.
Okay. Thank you.
Okay, but an important point is that we can prove that DeepOSets are universal approximators of continuous permutation invariant operators in this setting, from finite dimensional to infinite dimensional. The infinite dimensional to infinite dimensional case is still under work, okay? But in this particular case of regression, supervised learning, we can prove this theorem by combining the two universal approximation theorems, the one for deep sets and the one for DeepONets, and then using continuity. So, using continuity, all the operators are continuous. Then we can prove that indeed DeepOSets are dense in the space of continuous permutation invariant operators. So it basically inherits the universal approximation property of deep sets and DeepONets. Okay. So that's good to know. Okay,
Professor,
so
I had a small question, if you don't mind.
yes.
This is Varun from Brown.
Okay.
So is there like a specific requirement why you need to have the branch? Or could you not just use the embedding embedding with the trunk to get the output?
Well, the branch adds another layer of MLPs. For instance, another MLP. It could be something else, right? It doesn't have to be MLP, but that's a valid question. I mean, I could act directly on the latent space, yes, but the branch adds another layer of MLPs to improve the expressivity of the network.
Okay, and I had another question on the previous part where you said that your initial your input to latent space can be a function, whereas from the latent space to the output you need an operator. So
Yes.
is that a requirement, or is that something that works well?
So here is what happens in the representation theorem, okay? So this is inspired by the representation theorem. So, the representation theorem says that, you apply a function to each data point.
Yeah.
Okay? And then you pull them.
Mm-hmm.
Okay? And then you have to apply an operator that maps this finite dimension space to the infinite dimension space. So the composition of this operation, okay?
Okay, I understood.
Okay.
Okay, thank you.
No problem. So,
Ulysses, can I ask also a question?
yes.
So if I take the standard DeepONet,
Yes.
vanilla DeepONet, and obviously we have function to function, but we project it, right? So after the projection, we have a finite set of points for the function. Now, I can impose some equivariance, any equivariance that you, here you have set, but I mean, and that could sort of do the same thing.
Yes, but it doesn't have the permutation invariance bias, right? So this deep sets layer adds the permutation invariance bias and allows you to accept inputs of any size, which the standard DeepONet cannot do.
So it's a hardwire as opposed to penalizing, for example, to include a...
It's hardwired into the deep sets, yes.
Yeah, okay, yeah.
Yes. Yeah.
And you have the theorem also.
Yeah. So, okay. So it's a child of DeepONets, okay? It's, it's in the family, okay? But the original DeepONet cannot accept, of course, inputs of any size in the branch and does not have the permutation invariance bias. So, Okay, so it's still about the pooling. So like I said, the representation theorem is based on summing, okay? But you can use other things. So for instance, something that has been proposed in this paper down here is that you could use something very similar to attention. So you could work on pairs of points, of examples, and then your phi adds works on pairs of points of examples, okay? And then you can do this for any number. So you can do this for triplets, or 4 or 5. So when k is equal to n, then you essentially look at all possible permutations, which is very costly, of course. But if you if you do k equal to 2, it's still okay, even though it makes it n squared now in the number of examples. So that becomes like the transformer. In fact, this is very similar to self-attention. So self-attention is a special case of this. So they call it Janossi pooling. So we tried this one too in our experiments. Okay. All right. So here is the first experiment. So here we have, like in that paper that I mentioned, we have a hypothesis space which is linear space. I'm sorry, it's a space of linear functions, and W is randomly picked. So this can be any orientation. These functions can be in any orientation, but these are functions, okay, linear functions. So here the objective is to be able to train the DeepOSets to learn to perform this kind of linear regression from noisy data at test time. During training time, the data is noiseless. So we are going to produce the prompts by generating the data from the hyperplane noiselessly, okay? And then we're going to train on several different lines with different orientations, different hyperplanes with different orientations. And then at test time, I'm going to come with the data set from a different hyperplane, and I'm supposed to produce the line without any further training. So, it's a regression algorithm. So, I can come with data of any size from any hyperplane, and I'm supposed to produce the line. So like doing ordinary least square regression. This is a different one, but it's doing the same thing, okay? So in this experiment, we use 13 in context examples. The training time was 9 minutes, and I'll show you the size of the network in a second. But the training time was 9 minutes. The training loss was small. I'll show the errors as well. But that's the idea, is that you add noise. So in this particular example here, the noise was 0.1. Okay, so you're seeing the least squares result is the blue line, the ground truth is the black line, and the DeepOSets is the red line. So you can see that DeepOSets gets very close to the ground truth. In many cases, it's exactly the same. So let's see then the errors. Okay, so the MSE, which is the difference between the ground truth and the prediction, for d equal to 1 and d equal to 5, under different noise levels, okay, and also, so for each noise level, varying the number of examples in the test prompt. The training prompt was always 13, the length, but the test prompt is from a different size. You can vary the size, okay? So here we vary from 2 to 10, and we consider low noise, high noise, and then we look at the performance as a number of in-context examples for different noise levels. And then we also look at the performance at different noise levels for fixed number of in-context examples. All of this at test time, right? So for d equal to 1, we use from 2 to 10, like I said. For d equal to 5, we use from 6 to 10 because you cannot use less than 5. You know, the problem is you post. But so here what you're seeing is that for low noise, so okay, we are comparing also against the transformer, that transformer that I mentioned, okay? So what we are seeing is that for low noise, we are able to do a very good job, even with very few number of examples. At higher noise, we still do a good job, but is slightly less of a good job. So for low noise, I'm sorry, for high noise, you know, I may have gotten it backwards. So for high noise, we do a good job. All right. I mean, let's see the case d equal to 5, okay? So for the case d equal to 5, because d equal to 1 is easier, but, you know, for d equal to 5, we can see that the DeepOSets is the red, okay? So for high noise is the best, beats everybody. For the low noise, is not good, okay? But you can see that for fixed number of in-context examples, you see the same thing, okay? For high noise, it beats everybody. For lower noise, it is less effective, okay? And you can see that. But so this tells you that it's very robust to noise. The other things, including ordinary least square regression, they break down under noise, okay? Whereas the performance of DeepSets is much more flat with respect to the noise, okay? You know, you can see this, whereas the other guys are very sensitive to the noise. So that was an initial experiment we did. But if you look at now the actual values, we can see that the same thing I said. I mean, is that you know, under for d equal to 1, we do very well. By the way, right? For d equal to 1, we do very well. We beat everybody. But for d equal to 5, we're gonna beat the transformer under higher noise, but the transformer is gonna be better under lower noise. Okay, so it's a mixed bag. Okay, now what I want to show you is now the complexity. Okay, so we are comparing these results on accuracy, but now look at the complexity. Okay, this transformer model that was used had 22 million parameters, and they can do d equal up to 20. Okay, here we did only d equal to 5. So, you know, conceivably you could have used fewer parameters to do d equal to 5, but it's still 22 million. Okay, whereas the DeepOSets 72K. Okay, DeepOSets with k equal to 2, genomic pooling is a little larger because, of course, you look at all pairs. 84K, but also look at the training time. Okay, I mean, if you have to train such a transformer, okay, I mean 3 hours. Okay, but for DeepOSets 9 minutes. Okay, on GPU. And the complexity, like I said, it's always n squared for the transformer because you have to do it sequentially, you know. Whereas for the DeepOSets, after the first prediction, after the first query point, it's constant because you have already processed the prompt and you're just changing the query. So as a function of the size of the prompt is constant, okay? For the first prediction is O of n for, you know, just the k equal to 1. For k equal to 2 is O of n squared. But even in the case k equal to 2, it's still constant after the first query. And the memory for the transformer is also O of n squared because of the self-attention matrices, right? Whereas for the DeepOSets, again, it's constant. Okay, so for the transformer, when you increase the size of the prompt, the matrices are bigger. Okay, whereas for DeepOSets, it doesn't change. The architecture doesn't change. Okay, I mean, it's okay. And then the inference time per query. Of course, such a big transformer, is going to take much longer. So it's about 100 times slower to process this prompt, whereas for DeepOSets is almost instantaneous. Okay, because it's in parallel and it's a much smaller model. And then we still beat it, even though, of course, this is d equal to 1, okay? We still beat it in accuracy, okay? So I thought this result was kind of remarkable. I'm sure that you can, fine-tune this transformer approach and make it, use fewer weights, etc. But there's a limit what you can do. It's still a very simple problem, d equal to 1. But it shows a proof of existence, that we can do a better job with much less complexity. Okay. All right. The next example is learning polynomial regression. Now the hypothesis space is a polynomial functions, not just linear functions, polynomial functions. But you don't know the order of the polynomial. So it's not just the coefficients that you don't know. You don't know the order either. So the order can go from 1 to 10. So it could be from lines to parabolas to cubics, anything. Okay. So you're going to pick the coefficients randomly for the polynomials, and the order you're going to go from 1 to 10. Okay. And then you're going to test on order 6 polynomials. Okay. So we're going to have going to train on 20 examples, point, target, value, but we're going to test on 15 examples, 15 points, okay? So, and the training time is 2 minutes. We have, so the network doesn't know that it's order 6. It doesn't know it's a 6-order polynomial, okay? But you're going to give it the prompt. You're going to give it, these examples, these data points, okay? So in an ordinary regression problem, you'd have to select the order. So you're going to have some kind of grid search or some kind of a procedure to select the order of the regression, okay? But here the network is able to learn that directly from the prompt. So it's an example of multiple operator learning.
Ulisses, are the plots here for testing?
Yeah, for testing, yes.
Because if you look at the, let's say, 2-3 panel, it's totally wrong, right? It gives a linear polynomial.
Where?
2-3. Look at think of this as a matrix 3 by 3, 2-3.
Okay, 2-3 here, this one.
Yeah.
Here it failed, yes. So here, because the points are almost lined up.
So there is, I saw also the previously. So, but then it seems that there is outliers because there's most of all of them are good except one and so on. So it seems that there's an outlier, even in the linear regression, so something like that.
There could be outliers, yes, exactly. So those MSCs that I showed you were averages.
Yeah.
But here, yeah, exactly. So the points are kind of lined up. It fools the DeepOSets, right? It thinks it's more like a linear function. But once again, we are not doing any grid search or anything, right? So, and then the noise here is 0.1. So now if you look at comparison with, okay, so let me go back. So here we are looking at the DeepOSets with k equal to 1. We are looking at the what we call polyfit leave on out, which is we're gonna do grid search between 1 and 10 using the leave on out error to pick the order to do least squares regression, okay? And then we're seeing the ground truth. So this is the comparison. Now, of course, this polyfit will take much longer because you have to do, in fact, 10 regressions and then select the best one, right, according to the live on out error. And you will fail. I mean, you're going to get the wrong order often. So that's what we are seeing in the MSC. You know, the MSC of the polyfit will jump a lot. You know, it will jump a lot because this order estimation is a discrete estimation problem, and you'll be wrong sometimes. And then you can see that this is for low order polynomial and this is for high order. But what you can see is that the DeepOSets is flat. Okay, it's flat because it will not be wrong as often, or it will not be variable as variable. I should say it's not going to be as variable as a grid search. So so that's what you're seeing here, and then you're seeing here the complexity. It's O(n) cubed because we have to do n regressions, and so each one is O of n squared. Because you're doing least squares regression, and you build a matrix which is n by n. So it's O of n cubed, but this one here is O of n as before. Okay, the inference time is faster, and the test MSC is smaller. So of course, polyfit has no parameters or training time, but this is the comparison. So again, in a simple problem, and then but it shows the ability to do this automatic selection, right? Okay, so the last part of the talk is how can we apply this to PD operator learning. So here is ongoing work. I have very preliminary results, okay, but the goal again is ambitious. Okay, we want to apply this to realistic problems. We are still working towards that, but here I'm going to show you some simple PDs. Okay. Now, what does it mean? What does it mean to do in-context learning for PDs? Okay, so there was a paper, 2023, which I think is your former student, George, right?
Yeah, Yang Lu.
Yes, and then they proposed this approach in context learning for PD operators. So again, they're using transformers, right? But the rationale behind this is very similar. It's the same thing as before. You have a prompt where you have a condition, the input could be initial condition, for instance, for time evolution problem, and then you have the answer, which the answer could be the final condition, or it could be the entire solution, or something like that. And then your prompt consists of examples, the same way that you train normally a neural operator. You have to give pairs of examples of input and output. But here, these pairs of input and output go into the prompt. And then you have a query, which is a new condition, a new initial condition, or new coefficient function, etc. And the model is supposed to predict. Now, you can do this for a single PD, or you can do this for multiple PDs. So, single PDE, the prompt is always from the same PDE at training time and test time. That's not the interesting case. Okay, the interesting case is when you have multiple PDs and you train on a subset of these PD operators, and then you predict on a new PD operator by just having the data. Okay. So again, it's sort of like multiple operator learning or so-called foundation model, whatever you want to call it. But you're making predictions on things you have not seen before. So that's what we're going to try to do. And that creates a well-posedness question for, if you try to apply a regular DeepONet or neural operator in this multiple operator learning problem, that creates a well-posedness question because, from the same initial condition, you can have different evolutions, okay? Depending on the PD operator. So same initial condition, going to have different evolutions. So there is a well-posedness question. But in-context learning removes that because the PD operator can be disambiguated from the examples in the prompt, okay? So that is a benefit. If you do not do in-context learning, you have to have some kind of fine-tuning. You're going to have to fine-tune your model. You're going to have some kind of label, estimate a label for this new operator. Because otherwise, it's impossible to predict from the same initial condition, right? So, okay. So here we have to change the architecture a little bit. So, so here now the examples are discretized functions. So input and output. And then the query is a function also, discretized function, that goes into the branch, just like a normal DeepONet. And then you evaluate the output function via the trunk. So it's very similar to DeepONets, except that the prompt is encoded into this latent space and goes into the branch together with the query. Okay. So that's the basic idea. So it's a simple modification. And I'm going to show you some, like I said, some initial simple results where we use this architecture. Okay. So let's consider 4 problems. So the first is a Poisson boundary value problem, where you have 2 problems. You have the forward problem and the inverse problem. Forward problem, you're given the forcing function and you want to find the solution. And in the inverse problem, you're given the solution u of t and you want to find the forcing function that produces that solution, right? And it's a boundary value problem, but you don't know the values on the boundary. These values can change. So you don't have that information on the boundary. So that's the problem. And the second problem is again a boundary value problem. It's a simple reaction diffusion where the input is the coefficient function and the output is the solution. So that's the forward problem. Whereas the inverse problem, given the solution, find the coefficient function, okay? And now, not only the boundary conditions are unknown, but the parameters of the PD are also unknown. So, so that is the second problem. So, in fact, we have 4 problems. We have the inverse and forward for each of these 2 PDs. So we take these 4 problems from the paper by Young, okay? It's a subset of the problems they consider there. Here we have not implemented the Young, okay? So we are not showing the comparison with them, but we're going to show how accurate we can be, okay, for these 4 problems. We adopt then a similar experimental protocol to what they did, okay? So the prompt, in our case, contains 4 examples and 1 query. So 4 examples of input and output and 1 query input function during both training and testing, okay? And to generate the training data, for each of these 4 problems, we generate 100 different values of the parameters randomly. And for each set of parameters, we solve the PDE and discretize it at 100 locations, okay? And this is our training data. It's much smaller than what Young used. Remember that they are using a transformer. So, here So, okay, so then we train the DeepOSets using gradient descent, sampling batches, okay? And during testing, then we generate a prompt by randomly generating the parameters, boundary condition, etc., and generating the examples from that. Okay, so this is the test. So here are the results for the forward Poisson. So here we are seeing at the top graph, we are seeing the four examples, the top and the bottom. Okay, so the top and the bottom, you see the gray curves are the examples of the forcing function, and the solution at the bottom. Okay, so U0, these are the forcing functions. Okay, and then at the bottom you see the corresponding solution. So these are the gray curves. Okay, so for each gray curve you have a solution, and then the query is the blue curve. So it's a blue curve. At the bottom you're seeing the ground truth in black, and you're seeing the prediction in red. So we're seeing that it tracks it very well. Okay, so this is the forward problem. Now the inverse problem is harder. You can see that, you know, the solution varies more. Okay, and because the solution in fact is the forcing function. So this is backwards. Okay, at the top you have the solution, and at the bottom you have the forcing function. And then you're seeing that obviously the same thing. You're seeing the four examples at the top with the four targets at the bottom, and then a new query in blue at the top, and at the bottom you're seeing the ground truth and the prediction. Okay, so you can solve this inverse problem. And remember that you don't know the boundary conditions, even though here is kind of trivial, because you know you could look at the force, you could look at the solution in the forward problem. You could look at the solution. Okay, you see the boundary values. Okay, for the query. Of course, the network is not looking at that. I mean, you, as a human, could do that. But in the inverse problem, you don't know that at all. So I mean, you don't know the boundary conditions, but you can get it. And then we do the same thing for the other problem. Okay, so this is similar. So you have the coefficient function now and the solution for the forward problem, and it's a similar behavior. And for the inverse problem,
Ulisses here, it misses. If you go back, you see it misses the boundary conditions.
Yeah, it is incorrect here. Yeah, it's a little bit incorrect. Yes, you're right.
So but it's a boundary condition that it misses. That's the problem.
The boundary condition is not being forced.
Yeah.
Yes, because that was the setup for the problem.
I think it's because you can see the equidistant, that black line, right?
Yeah.
Is between those two other gray lines. So it's kind of tries to compromise between the two gray lines if you look at zero.
It could be, yes. Yeah, it could be. And it's not being forced, you're right. So, you know, it doesn't know what the boundary condition is. So this needs to be improved. So with more training, here we're not using a very large training data set. We need to use more training to improve this, yes. And then here is the opposite. Okay, so solution and the coefficient function. So okay, I'm sorry. Here it's forcing function solution, and then let me go back here. So this is the forward Poisson, the inverse Poisson, this forward reaction diffusion and inverse reaction diffusion. Okay, so this is what it is. Okay. So in conclusion, okay, so we are proposing the convergence of ICL, permutation invariance, and operator learning. So these three actors have not played in a play together so far. Okay, so you know, only two of the three but now we're putting the three together, okay? And then, so we proved that DeepOSets is a universal approximator for continuous permutation-invariant operators, acting in finite data spaces. So we haven't proved it yet for infinite dimension spaces, okay, on both sides. So these preliminary experimental results, show good noise robustness, efficiency, without compromising accuracy too much. And in fact, even in some cases, being more accurate. It requires fewer parameters, transfer, etc. than the transformer. It has linear time in memory, or even constant time after the first query at inference time. It can perform automatic model selection or multiple operator learning. So this is what they talk about these days when they talk about foundation models, right? It's a hammer that you can use to hammer any nail that appears. Okay, it's still a little far from that, but that's the goal. And then we also showed some simple results for PDs. So this is still ongoing work. Okay, so now with that, I open for questions. We don't have a lot of time left, but if you have questions, be happy to answer.
Thank you so much, Ulisses. Don't worry, if we need more time, we can stay a few more minutes. So it's not a rush. Do we have any questions from the audience?
Yes. Hi, Ulysses. This is Kyle from Brown.
Hi, Kyle. Nice
Hi.
to see you. Yeah, nice to
Yeah.
meet you in person, or virtually at least.
Yeah.
Yes.
Yeah, nice to see you. So thank you so much for this great talk. I really like it, and I learned a lot from this. So just to follow up on your comparison between the DeepOSets model and the transformer, I think maybe you could even replace the DeepSets component of the DeepSet model with, for example, a transformer encoder. Like without the position embedding is also permutation invariant, so that might combine the two.
Absolutely. Yeah, that is a very good point. There is something called a set transformer.
Yeah.
Yes, and then so it accomplishes the same thing. Is the transformer can do permutation invariance, but it doesn't enforce it. It's not a bias into it. It just can process out of order. But it can also do, of course, a variable number of examples. That's what they use. But the set transformer is a transformer that can operate in parallel with a built-in permutation invariance bias. Yes, and so this is something we are looking into too. But originally the goal of this was to see if we can do this with a very simple architecture. Okay. But of course, I'm sure that as we look into more complex problems, we might have to use a set transformer, for instance, for the encoder, right? The decoder would still be a DeepONet, okay? But yes, so yeah, you have a very good point. Yes, absolutely. Yeah.
Ulysses, in terms of the cost, the linear cost and the memory, a Mamba used as an operator, because that's what we do. We have something called Depot Mamba. I don't know if you've seen that paper.
I have heard about Mamba, but not Depot Mamba.
Depot Mamba is in the branch. That gives you linear cost and very small memory signature.
Right. I have to look into that too. Yes. Some people have been asking me about Mamba. Yes.
Yeah, really good accuracy and a long time integration. Many different advantages.
We are not married to DeepSets necessarily, but we are married to permutation invariance bias.
Yeah, the representation theorem is very powerful.
Yeah, the representation theorem, yes.
The decomposable, the decomposition.
Yeah, exactly. Yeah, that's the inspiration.
Thanks for coming, Ulisses. A great talk.
Thank you very much again. It's always good to see you, George, and everybody here. If you have more questions later, feel free to email me, or just I'll be happy to answer.
Great. Thank you so much, Ulisses. Let's see if we have any other questions from the audience. So,
Everybody
apparently,
understood everything, no questions.
apparently we don't know. Okay. Thank you so much for your time today, and thank you so much everyone for joining us this Friday and with this week. Oh, you have a question,
on my
Sasha?
camera.
There's a question?
There's a question?
Yeah, just a second. If it works, I'm not sure. Oh, yeah, here it is. I am Sasha, postdoc at Brown. I understood that the context, the query could be a boundary condition, right? Or different so realizations of the boundary
Yes,
conditions.
exactly. So it depends on how you set up your question, right? So you could be predicting from the boundary conditions to the solution, where the boundary conditions might include initial conditions as well, perhaps. But in the PD operator case, we typically try to predict from a function to a function, right? So, but not necessarily. I mean, you could also be predicting from finite dimensional information to a solution. Yeah.
Yes, very interesting. So the question would be, so say we interpret the queries as different kind of boundary conditions. Could that also work for different geometries of the boundary itself?
Yes. So for now, of course, you saw extremely simple examples of PDs, but the ultimate goal is to be able to apply this to realistic problems. In which case, yes, there's no constraint on the geometry. It's totally agnostic to the geometry. It's meshless, right? So it's just like, so DeepOSets is just like pins. It's meshless, right? So
what I did not quite understand is how the different geometries of different boundaries would be encoded in that. I understand the DeepOSets would be somewhat agnostic to that.
Good point. So this is a good point. Maybe if you can encode the geometry, it would improve the accuracy. But this would have to be checked on a case-by-case basis. But in principle, you could have just the information on the boundary, because remember, you're training right with these prompts, and then you're giving a new prompt. If you vary the geometry for the test prompt, that's probably a very challenging problem. Okay, but if you don't vary the geometry, it's for the new prompt, the network should be able to do it. If you vary the geometry, you probably need to test on different. You need to train on different geometries. Yes, so you have to encode the geometry. So, I think, yeah, it's a good question.
Okay, but that would then be in the branch, right, of the DeepOSets, the underlying.
All this information from the prompt goes into the branch. The trunk is just to evaluate the yes. Yeah.
Okay, thank you.
Okay. No problem.
Great, thank you so much. So with this, I think that we can close this session.
Okay. So
thank you.
Everybody have a nice weekend and see you soon.
Okay, thank you everyone. Bye.